What if the universe harbored a world completely covered by water, an endless ocean where not a single island breaks the surface? Kepler-22b is one of the most fascinating candidates for that scenario, an exoplanet that has captured the imagination of astronomers and dreamers alike. Discovered over 600 light-years from Earth, this mysterious planet orbits a star similar to the Sun and lies in the zone that scientists call habitable. But what does that really mean? Could there be an ocean so vast that it makes our seas look like mere puddles? The search for life beyond Earth leads us to pose profound questions about the nature of planets and their possibilities. Is it possible that Kepler-22b harbors some form of life in its endless waters? What conditions are needed for liquid water, that essential ingredient for life as we know it, to remain stable on such a distant world? Imagining a planet where geography is defined not by solid ground, but by endless blue depths, challenges everything we know about habitable places in the cosmos. Unlike other exoplanets discovered so far, Kepler-22b stands out for one key reason. It possesses characteristics that make it one of the most promising places to find environments similar, at least in part, to our own planet. But the differences are staggering. Its size, its unknown atmosphere, and the possibility that there are no continents highlight a radically different scenario from Earth. What would life, if it exists, be like on a world where the horizon of land is never seen and where each dawn reveals only more water as far as the eye can see? The study of Kepler-22b not only helps us understand the diversity of planets that exist in the galaxy, but it also forces us to rethink what we consider habitability. Is Earth an exception or just one more version of an almost infinite diversity of worlds? In the upcoming sections, we will explore the data, hypotheses, and mysteries behind this astonishing oceanic planet. But today, the question remains in the air. What secrets does Kepler-22b hide beneath its mantle of endless water? What led humanity to discover a planet as distant as Kepler-22b? The key lies in curiosity and technology. In the early 21st century, astronomers searched for new worlds beyond the solar system using the Kepler Space Telescope, a mission specifically designed to hunt for exoplanets. But how do you detect something so small and distant, hidden among the immense darkness of space? The answer lies in patience and meticulous observation. Scientists monitored thousands of stars, hoping to perceive a subtle decrease in their brightness, an almost imperceptible signal that a planet was transiting in front of its star, blocking a tiny fraction of its light. It was thus, after carefully analyzing the data, that in 2011 the discovery of Kepler-22b was announced. This event marked a turning point in the search for new worlds, as Kepler-22b became the first exoplanet detected in the habitable zone of a star similar to the Sun. This means that, theoretically, it could harbor liquid water on its surface, one of the essential ingredients for life as we know it. Why was this finding so relevant? Because it opened the door to the real possibility of finding Earth-like planets, increasing the hope that we are not alone in the universe. But the discovery was more than just a stroke of luck. It required years of observation and the analysis of tiny variations in the data collected by the Kepler telescope. Astronomers had to rule out other possible explanations for the decrease in the star's brightness. Could it be sunspots, instrumental errors, or even another stellar phenomenon? Only after confirming that the observed pattern repeated at regular intervals and with the help of ground-based telescopes to verify the results, could scientists confirm the existence of Kepler-22b. This discovery not only demonstrated the effectiveness of the transit method, but also inspired a new generation of research dedicated to the search for habitable exoplanets. The finding of Kepler-22b was, in a way, like finding a needle in a cosmic haystack. A world over 600 light-years away, detected thanks to human perseverance and ingenuity. How many other secrets await revelation in the vastness of space? The story of Kepler-22b reminds us that every small clue can lead us to extraordinary discoveries.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this star odyssey.
Where is Kepler-22b really located in the vastness of our galaxy? This is a fascinating question because when we talk about exoplanets, we automatically think of distances that challenge our imagination. Kepler-22b resides in the constellation Cygnus, a region of the sky that, from Earth's perspective, seems calm but actually harbors an astonishing amount of mysteries. Now, how far is this world from us? Approximately 600 light-years. To put it in perspective, the light we see today from its host star began its journey when the dynasties of the Renaissance still reigned on Earth. If we could travel at the speed of light, it would take us 6 centuries to get there. But what does it mean to be 600 light-years away? In galactic terms, Kepler-22b is relatively close within the Milky Way, which measures about 100,000 light-years in diameter. We could imagine our galaxy as a gigantic city, and Kepler-22b would be like a neighborhood located just a few blocks from where we live, at least if we consider the scale of the entire galactic neighborhood. However, for current human technology, that journey remains unimaginable. The location of Kepler-22b reminds us of how vast our cosmic home is, and how small we are on the universal scale. The Milky Way is made up of hundreds of billions of stars, and Kepler-22b orbits one of them in one of the spiral arms, the so-called Orion arm. This arm is like a main avenue where our own solar system is also located. Isn't it incredible to think that, in the vastness of the galaxy, both Earth and Kepler-22b share the same galactic neighborhood? Although separated by an overwhelming distance, both planets are part of the same spiral structure that winds through the galaxy like a majestic dance of stars and planets. When we ask ourselves if we could ever visit such a distant planet, the reflection on the current limits of space exploration inevitably arises. Our technology has barely allowed us to explore the far reaches of the solar system. And yet, thanks to observatories like Kepler, we can detect worlds as distant as Kepler-22b. Thus, its location in the Milky Way is not only an astronomical fact, but also a reminder of the frontiers we still have to cross and the dreams that humanity keeps alive by looking toward the stars. What type of star orbits Kepler-22b? The answer is fascinating. Kepler-22, its host star, is a yellow dwarf, very similar to our own Sun. However, what does this really mean? Yellow dwarfs are stars of intermediate size and temperature, capable of providing a stable amount of energy for billions of years. This stability is key for the development of habitable conditions on the planets that surround them. Kepler-22, in particular, has about 10% less mass than the Sun and is slightly cooler, which directly influences the climate and potential habitability of Kepler-22b. Is Kepler-22 then an exact copy of our Sun? Not exactly. Although they share many characteristics, Kepler-22 emits slightly less intense light and its surface temperature is lower, around 5,500 degrees Celsius, about 200 degrees less than the Sun. This small difference may seem insignificant, but in astronomical terms, it is crucial. It determines the distance at which a planet must be located to receive the right amount of heat and light. That's why Kepler-22b orbits closer to its star than Earth does to the Sun. But the energy it receives is similar. What age are we talking about when we think of Kepler-22? Astronomers estimate that this star is about 6 billion years old, somewhat older than our Sun. This fact is vital because it indicates that Kepler-22 has had enough time to provide a stable environment, allowing its planets to evolve without major cosmic upheavals like explosions or sudden variations in radiation. Thus, the long life and relative calm of Kepler-22 increase the chances that Kepler-22b maintains a favorable environment for liquid water and perhaps for life. To better understand the role of Kepler-22 in this system, Let's imagine that the star is a large campfire in the center of a cosmic campsite. If you sit too close, the heat is unbearable. If you move too far away, the cold is total. Kepler-22b seems to be at just the right point, neither too close nor too far from its energy source. In summary, the nature of Kepler-22 as a yellow dwarf, its advanced age, and its stability make it an ideal host for a planet like Kepler-22b to spark scientific curiosity about the possibility of other habitable worlds in the universe. How big is Kepler-22b really? This question has intrigued scientists and space enthusiasts since its discovery. To get an idea, let's think of Earth as a blue marble. Now, if we placed Kepler-22b next to it, it would look like a tennis ball beside that marble. The radius of Kepler-22b is about 2.4 times greater than that of Earth. This means that if we walked along its equator, we would cover a much longer distance than the circumference of the world we know. But does this mean it is simply a larger version of our planet? The mass of Kepler-22b is another fascinating mystery. Astronomers have not been able to measure it directly, but they estimate that depending on its composition, it could be between 6 and 36 times the mass of Earth. If the planet were primarily made of rock, it would be immensely dense, like a colossal version of our home. However, if water and lighter elements dominate, its mass would be closer to the lower end of that estimate. Imagine trying to lift a rock on Earth and then trying to lift that same rock on Kepler-22b. The difference in weight would be noticeable, and our bodies would feel gravity in a completely new way. Does this great size affect surface gravity? Absolutely. If Kepler-22b has a composition similar to Earth, its gravity could be about double or even more. This would have direct consequences for any form of life, for the formation of oceans, and for the atmosphere. Under greater gravity, objects would fall faster and moving would be more difficult. Even the simple act of walking would require much more energy. Native creatures, if there are any, might be more robust and compact, adapted to withstand a more intense gravitational force. However, the size and mass of Kepler-22b not only make it interesting from a physical perspective, but they also influence its potential habitability. A larger planet has a better chance of retaining a dense atmosphere and maintaining internal heat for billions of years. Could this create ideal conditions for life? The answer largely depends on details we still do not know, but understanding the size and mass of Kepler-22b helps us place it on the map of potentially habitable worlds and dream of what might lie beneath its immense ocean. What does it mean for a planet to have a year? On Earth, a year is the time it takes our planet to make a complete orbit around the Sun. But on Kepler-22b, this cycle is different. Orbiting at a greater distance from its star than that which separates Earth from the Sun, Kepler-22b takes about 390 Earth days to complete an orbit. Although its year is just slightly longer than ours, the fact that it resides in the so-called habitable zone of its system makes it a particularly interesting candidate for those searching for worlds capable of hosting life. But how does Kepler-22b move in its orbit? Scientists have calculated that its orbit is nearly circular, meaning the distance between the planet and its star hardly varies throughout the year. This stability is crucial. It prevents extreme temperature changes and ensures more predictable conditions on the surface. If the orbit were very elliptical, the seasons could be more extreme and therefore less favorable for life as we know it. A fascinating tidbit is that the distance from Kepler-22b to its host star is approximately 10% greater than the distance between Earth and the Sun. However, its star is a bit cooler and smaller than our Sun, which balances the amount of energy the planet receives. It's as if Kepler-22b is in a temperate zone, neither too close nor too far, a place where water, if present, could remain in liquid form throughout its year. Now, how does the length of the year and the orbit of Kepler-22b affect the possibility of life? A year of nearly 400 days means that the seasonal cycles would be somewhat longer than on Earth, but not radically different. This could allow for the development of stable ecosystems, as long as other favorable factors are present. Thus, the orbital dance of Kepler-22b not only determines the length of its years, but also influences its climate, its potential habitability, and ultimately, the fascination it sparks among astronomers around the world. What would we find if we could descend onto the surface of Kepler-22b? This is one of the great mysteries that intrigues astronomers. Although there is no direct image of the planet, the collected data suggests that there are no continents or mountain ranges like those on Earth. Instead, the most accepted hypothesis is that Kepler-22b is completely covered by a vast, endless ocean, a watery world where no solid ground would be in sight. If we could fly over this exoplanet, we would most likely only distinguish an immense blue mantle, reflecting the light of its host star. Is it possible that there are something like islands or land masses emerging from the waves? So far, current models indicate that the pressure and temperature on the surface would be so compatible with liquid water that the formation of large land areas would be very unlikely. In fact, some scientists compare Kepler-22b to a gigantic version of Europa, Jupiter's moon, but on a much larger scale and potentially with an even deeper ocean. This ocean is estimated to be hundreds of kilometers deep, compared to the mere 11 kilometers of the Mariana Trench on Earth. But what would it be like to dive into that ocean? The exact conditions remain a mystery, although it is believed that the pressure at the bottom of this global ocean would be monstrous, far exceeding what we find in the most extreme depths of Earth's oceans. Beneath that enormous column of water, there could be layers of ice formed by the pressure, separating the liquid water from a possible rocky core. In other words, we could be facing a planet where water takes on forms and behaviors unknown to us, with areas where chemistry and physics challenge what we observe on Earth. Could there be any form of life floating in those infinite waters? The absence of solid ground, mountains and volcanoes makes the dynamics of the surface radically different. Currents, winds, and the possible presence of titanic storms would set the rhythm of a constantly moving planet. However, the presence of such an extensive ocean opens a fascinating door. If the right conditions are met, this world could be a true natural laboratory for life, perhaps even more diverse in its depths than we can imagine. Thus, Kepler-22b remains one of the most intriguing scenarios to investigate what surface conditions might be like on a watery planet outside the solar system. Is it possible for there to be a planet completely covered by water, with no trace of land? This is the fascinating hypothesis surrounding Kepler-22b. The idea of a global ocean so vast that all the seas of Earth would seem like puddles in comparison. What led scientists to think that Kepler-22b could be a world of infinite ocean? The key lies in its size, its location in the habitable zone, and the way it interacts with its host star. Kepler-22b has a radius approximately 2.4 times greater than that of Earth, suggesting it could be a super-Earth or even a mini-Neptune. But why think that its surface is dominated by water and not by rocks or gas? Planetary models indicate that, at this size and with the estimated density, it is unlikely to be a rocky planet like ours. Instead, it is more likely to be composed of a thick layer of liquid water or ice, enveloping a solid core or perhaps a mixture of both. This possibility has led astronomers to imagine a world where water is endless, where there are no continents, no mountains, no deserts, just an infinite ocean. What would such an ocean be like? On Earth, the deepest point of the ocean, the Mariana Trench, reaches almost 11 kilometers deep. But on Kepler-22b, the water could cover the planet with hundreds, perhaps thousands of kilometers of thickness. At such depths, the pressure would be so extreme that the water could take on exotic forms, such as the so-called high-pressure ice, a type of ice that forms not from cold, but from immense pressure. This phenomenon, impossible on Earth, could be common in an oceanic world like this. Can you imagine a sea so deep that not even the brightest light from its sun could reach it. What are the implications of such a planet for life? The existence of a global ocean increases the chances of liquid water, a fundamental requirement for life as we know it. However, the absence of solid land poses unique challenges. For example, on Earth, continents act as sources of essential minerals that reach the ocean through rivers. If there are no emergent lands on Kepler-22b, how would these nutrients be distributed? Some scientists believe that the interaction between the ocean floor and the planet's core could supply this need, as occurs in the hydrothermal vents of our own deep ocean. The hypothesis of the infinite ocean remains a conjecture, based on indirect observations and the best available simulations. But it opens the door to exciting questions. Could there be creatures adapted to the darkness and pressure of an endless sea? Would it be possible for life to evolve in an environment so different from ours? Kepler-22b invites us to imagine not only other planets, but other types of worlds, challenging our understanding of what it means to be a habitable planet. When we think about the temperature of a distant planet, the key question is, could it be warm enough or cold enough to allow life as we know it? Kepler-22b has sparked the curiosity of the scientific community precisely because its estimated temperature is, at least in theory, in a surprisingly similar range to that of Earth. But how do astronomers calculate the temperature of a world they have never visited? The answer is a mix of science, deduction, and a bit of imagination. They use data about the planet's distance from its star, the luminosity of that star, and its hypothetical atmosphere to estimate the so-called equilibrium temperature. It's like trying to guess the temperature inside a house by only looking from the outside, observing how brightly the sun shines and assuming whether the windows are open or closed. In the case of Kepler-22b, scientists have calculated that the equilibrium temperature hovers around 22 degrees Celsius. Does that mean we could enjoy a temperate climate on its surface, like an eternal spring? Not necessarily. This value assumes that the planet has an atmosphere similar to Earth's and reflects a similar amount of light. If its atmosphere were denser or had greenhouse gases like carbon dioxide in large quantities, the actual temperature could rise much higher. Conversely, if the atmosphere is thin or reflects more radiation, the planet could be much colder. In short, the actual surface temperature remains a mystery, although the conditions seem promising. But why is temperature so important when we talk about an oceanic world? The answer is simple: liquid water. The temperature must be maintained within a narrow range so that water does not evaporate or freeze completely. On Earth, that range is what allows life as we know it. If Kepler-22b maintains a similar average temperature, it's possible that its infinite ocean is in a liquid state, covering the entire surface of the planet. This would open the door to the existence of complex ecosystems, albeit different from those on land. However, there are additional factors we must consider. For example, how the planet distributes heat across its surface. If it rotates slowly, or if its atmosphere is very dense, there could be significant temperature differences between day and night, or between the equator and the poles. Are there titanic storms mixing the heat, or frozen water zones at the extremes? Each of these variables influences habitability. Thus, while the calculated temperature gives us hope, the reality could be much more complex, filled with nuances yet to be discovered. Kepler-22b remains an enigma, but its possible temperate climate places it among the most intriguing candidates in the search for habitable worlds. What would happen if an entire planet were covered by an ocean and, in addition, wrapped in an atmosphere completely different from ours? That is one of the great mysteries surrounding Kepler-22b. Although it has not yet been directly detected, scientists have developed fascinating hypotheses about the possible atmosphere of this enigmatic world. Given its size, larger than Earth, and its distance from its host star, Kepler-22b, is believed to potentially possess a gas envelope much denser than that of Earth. Now, What would this imply for a planet of infinite ocean? If the atmosphere of Kepler-22b were similar to that of Earth, we could imagine a blue sky and white clouds. However, many models suggest that its atmosphere could be rich in water vapor, generating permanently overcast skies, endless rain, and overwhelming humidity. Would it be possible to breathe there? Probably not. Some experts suggest that, being a more massive planet, it could retain light gases like hydrogen and helium for billions of years, forming a much thicker and more opaque atmosphere. This would make Kepler-22b a suffocating and mysterious place, more akin to Neptune than to our own world. The chemical composition of this atmosphere could be the key to understanding its habitability. If water vapor predominates, ideal conditions for a kind of natural greenhouse effect would be created, increasing the planet's surface temperature. But if, instead, the atmosphere is mostly composed of hydrogen, the light reaching the surface would be diffuse, and the color of the sky could range from pale blue to greenish or even pinkish tones, depending on the compounds present. This environment could be hostile to life as we know it, but perhaps ideal for completely different forms of life, adapted to high pressure and low light. Could life exist in such a different and dense atmosphere? The answer is not simple. On Earth, there are microbes capable of surviving in extreme environments, from acids to places with very little oxygen. On Kepler-22b, if the atmosphere is rich in water vapor and has high pressure, we could imagine organisms floating in the upper layers, similar to the bacteria that inhabit Earth's clouds. However, if the atmosphere contains a lot of hydrogen, the chemistry of life would need to be radically different. Thus, the potential atmosphere of Kepler-22b is not only a barrier, but also an invitation to imagine new forms of existence in the vast universe. Is it possible that thousands of light years away, there exists a planet that shares more than one characteristic with Earth? Kepler-22b has captured the imagination of astronomers and the curious alike precisely for that reason. One of the most notable similarities is its location in what scientists call the habitable zone of its system. This band is, in essence, the region around a star where temperatures allow for the existence of liquid water on the surface, something fundamental for life as we know it. Just as Earth is at the right distance from the Sun to be neither a scorching desert nor a frozen sphere, Kepler-22b also seems to have won that cosmic lottery. But what about its size? Curiously, Kepler-22b has a radius approximately 2.4 times greater than that of Earth. Although this makes it a super-Earth, the difference is not so vast when compared to the gas giants of the solar system, like Jupiter or Saturn. This means that, while Kepler-22b is larger, its density and composition could be closer to those of our own planet, rather than resembling those of a gas world. It's as if nature used the same recipe as Earth, just doubling some ingredients. Another fascinating similarity lies in the length of its year. Kepler-22b completes an orbit around its star in about 290 Earth days, quite close to the 365 days it takes Earth to orbit the Sun. This implies that the seasons, if they exist on Kepler-22b, could follow rhythms similar to ours, which in turn would influence the stability of its climate. Could a year of less than an Earth year influence the potential habitability of a distant world? Finally, scientists suspect that Kepler-22b might be covered by vast oceans, which echoes the fact that Earth is known as the blue planet because water dominates its surface. While on Earth oceans cover approximately 70% of the globe, the hypothesis for Kepler-22b suggests that water could form an even more global layer, enveloping the entire planet. Thus, both worlds would be true oases in the vastness of space, with water as a central element for life and evolution. Isn't it amazing to think that, despite the distance and the difference in history, Kepler-22b and Earth might share more than one secret in common? What makes Kepler-22b so different from Earth, despite both being located in the so-called habitable zone? Although they appear to share some similarities, the differences between these two worlds are profound and decisive. For example, While Earth is a rocky planet with continents and oceans covering most of its surface, the most accepted hypothesis about Kepler-22b suggests that it could be a true water world, a planet completely covered by a vast ocean with no land in sight. Imagine an ocean so extensive that not a single island emerges from its waters, an endless sea where the idea of shore simply makes no sense. But what about gravity? Here we find another fundamental difference. It is estimated that Kepler-22b has a radius approximately 2.4 times greater than that of Earth, which implies a significantly stronger surface gravity. This means that any form of life that could exist there would have to adapt to an environment where moving and rising is much more difficult. On Earth, we humans jump and run thanks to our moderate gravity, but on Kepler-22b, even a small jump could feel like we are carrying an invisible backpack full of stones. This greater gravity would also affect the atmosphere and pressure at the surface, making the air, if it exists, much denser than what we breathe here. And what about the planet's internal composition? Earth has a metallic core and a rocky crust, allowing it to have tectonic plates and volcanoes. However, on Kepler-22b, current models suggest it might lack a solid surface. Some scientists believe that beneath its infinite ocean, there could be a high-pressure ice layer, separating the liquid water from a rocky or metallic core. In other words, it would be as if beneath the Antarctic Ocean, there exists an ice layer so dense and thick that not even the planet's internal heat could completely melt it. This vastly different internal structure would have profound implications for geological dynamics and the possibility of chemical cycles essential for life. Another intriguing question is what the climate and atmosphere would be like. While Earth enjoys an atmosphere rich in oxygen and a climate regulated by the interaction between oceans and continents, Kepler-22b, being covered only by water, would have a completely different global climate. Without continents to slow down winds or influence currents, we could expect colossal storms and much more extreme weather systems. Additionally, the composition of its atmosphere remains a mystery. It could be made up of gases that on Earth would not be compatible with life as we know it. In short, although Kepler-22b and Earth share certain aspects, such as orbiting a star similar to the Sun and being within the habitable zone, the key differences between the two planets make them radically distinct worlds. Kepler-22b challenges us to imagine completely new scenarios for life and exploration, expanding the boundaries of what we understand as a habitable planet. What does it really mean for a planet to be in the so-called habitable zone? It's an essential question when we talk about distant worlds like Kepler-22b. The habitable zone, also known as the Goldilocks zone, is a band around a star where conditions could be just right for liquid water to exist on the surface of a planet. It's neither too hot nor too cold. It's, in a way, the perfect midpoint, like when you taste a soup and it's just at the ideal temperature. But why is liquid water so important? Because, at least on Earth, water is the basis of all life we know. So finding a planet in this zone is like discovering a key clue in a cosmic treasure hunt. Kepler-22b orbits within the habitable zone of its host star, Kepler-22. But does this guarantee the existence of oceans and life? Not necessarily. Being in the habitable zone is just the first requirement. Imagine you have all the ingredients for a cake, but that doesn't guarantee the cake will turn out delicious. You still need to mix them properly and bake them at the right temperature. Similarly, although Kepler-22b receives a similar amount of energy to what Earth receives from the Sun, factors like atmospheric composition, pressure, and the presence of the right chemical elements are also crucial. Can there be habitable worlds outside this zone? It's possible, but much less likely. A planet that orbits too close to its star would face hellish temperatures, where water would quickly evaporate. Conversely, a world too far away would be a frozen desert, where water could only be found in ice form. That's why the habitable zone is such a relevant concept in the search for extraterrestrial life. It's the range where the existence of liquid water is viable for long periods of time. However, the habitable zone is not an absolute guarantee of habitability. There are many nuances. For example, a planet's atmosphere can act like a blanket, trapping heat and allowing water to remain liquid even at the outer edge of the habitable zone. Conversely, a too thin atmosphere could cause water to freeze even while being inside the zone. Thus, Kepler-22b shows us that being in the habitable zone is like receiving an invitation to an exclusive party. It's a good start, but to truly enjoy the event, many other factors must align perfectly. Why has Kepler-22b captured the attention of the global scientific community in the search for life beyond Earth? The answer begins with its privileged location in the so-called habitable zone, a special band around a star where conditions could allow for the existence of liquid water on the surface. Water, as we know, is the fundamental ingredient for life as we understand it. If a planet can harbor this resource, it becomes a top candidate for astrobiological exploration. But is it enough to be in the habitable zone to think about life? Astronomers have identified thousands of exoplanets, but very few possess as many promising elements as Kepler-22b. Its size, larger than Earth but much smaller than gas giants, opens the possibility that it has a solid surface, or, at least, a deep and global ocean. This sets it apart from planets that, due to their composition or proximity to the star, are too inhospitable. The combination of factors, such as an estimated suitable temperature and a stable orbit, makes it a natural laboratory to imagine different scenarios of habitability. A crucial aspect lies in the fact that Kepler-22b orbits a star similar to the Sun, suggesting that it receives a comparable amount of energy to that which reaches Earth. This raises a fascinating question. Could biological processes analogous to those on Earth occur in such a different environment? The search for life beyond the solar system requires these bridge worlds, places that are not identical to Earth, but also do not stray too far from what biology needs to thrive. Thus, Kepler-22b represents a valuable opportunity to test hypotheses about how life might adapt to different planetary conditions. Finally, the importance of Kepler-22b transcends mere scientific curiosity. Each discovery surrounding this planet helps us better understand our own existence in the universe. If we manage to detect chemical or atmospheric signals suggesting biological activity, it would forever change our perception of cosmic loneliness. Are we truly alone, or are there other worlds where life has found its own path? Kepler-22b is a key piece in this great puzzle, and its study is an essential step in answering one of humanity's deepest questions. How is it possible to detect a planet that we will never see directly with our eyes? This question has fascinated astronomers for generations. Exoplanets, like Kepler-22b, are so far away and so faint next to their bright stars that, in many cases, they are practically invisible. However, modern astrophysics has devised ingenious methods to reveal their existence, using subtle clues in light and motion. One of the most successful methods is the transit method. What does it consist of? Imagine you are observing a light bulb, and suddenly, a tiny speck of dust passes in front of it, blocking a minimal fraction of its light. When a planet crosses in front of its star from our perspective, the amount of light we receive decreases slightly. This drop, although barely perceptible, can be detected by extremely sensitive instruments. Each time the planet completes an orbit and crosses again, this pattern repeats, allowing scientists to calculate the size, orbit, and even the atmosphere of the exoplanet if the star's light passes through its gaseous layer. But what if the planet never passes directly in front of its star from our point of view? This is where the radial velocity method comes into play. Stars, far from being static, wobble slightly due to the gravity of the planets orbiting them. These movements, although tiny, cause changes in the frequency of the star's light, an effect known as the Doppler shift. It's like hearing the change in pitch of an ambulance siren as it approaches and moves away, but applied to light. By analyzing these changes, we can infer the presence of invisible planets, their mass, and the shape of their orbits. Another intriguing method is gravitational microlensing. Can gravity be used as a magnifying glass? The answer is yes. When a star with a planet passes directly in front of another more distant star, the gravity of the first acts as a lens, amplifying the light of the background star. If there is a planet in the equation, it will create a small detectable distortion in brightness. This technique has allowed the discovery of planets in regions of the galaxy that are impossible to study otherwise. Finally, there is the direct imaging method. Although extremely difficult, technological advances have allowed, in rare cases, to photograph exoplanets by blocking the light of the host star, somewhat like covering the focus of a flashlight to see what is around. However, this is only possible with large planets that are far from their star. What do all these methods tell us? That each discovered planet is the result of decades of ingenuity and precision, and that the universe keeps its secrets, but also leaves traces for those who know where to look. Observing a planet 600 light-years away presents challenges that may seem insurmountable. How is it possible that we know so much about a world we have never visited? The reality is that astronomers only have very limited pieces of the puzzle. Detecting an exoplanet like Kepler-22b is a monumental achievement, but obtaining precise details about its atmosphere, surface, or even its true composition is a task much more complex than most imagine. Current tools, like space telescopes, function as if we were trying to study the silhouette of a fly perched on a light bulb kilometers away. The light that reaches us is greatly diminished and often contaminated by the host star itself. Can we fully trust the data we obtain? The answer is no, at least not in all aspects. The most common observation methods, such as planetary transit, only reveal a fraction of the information. For example, when a planet passes in front of its star, the brightness subtly decreases, and scientists can estimate the approximate size of the planet. However, this method has its limitations. It tells us nothing about the exact composition of the planet, whether there are actually oceans on its surface, or if there is a dense atmosphere. Additionally, errors in interpretation can easily arise, as any small flaw in measurement can greatly distort the results. Another fundamental limitation is time. Transits of a planet like Kepler-22b occur only once every about 290 Earth days, meaning scientists must wait nearly a year to collect a new signal and confirm their observations. Imagine trying to piece together a detailed portrait of a city by only seeing it for a few seconds each year. That's how fragmented the information we receive from these distant worlds is. Confirming any discovery requires years of repeated observation and enormous analytical work to rule out errors or phenomena that may mimic a planet's transit. Finally, current technology limits us in the most essential ways: the resolution and sensitivity of our instruments. Although space telescopes have advanced remarkably, we still do not have the capability to directly observe the surface of such distant planets or analyze their atmospheres in detail. Scientists rely on models and simulations to fill in the gaps of information, but these models are only as accurate as the data they receive. In summary, studying an exoplanet like Kepler-22b is like trying to decipher the plot of a book by reading only a few scattered lines. Each advance is a step closer to understanding, but for now, most of the secrets of these worlds remain beyond our reach. What makes a planet truly special in the search for life? The answer often revolves around the presence of liquid water. But why is this simple compound so essential? Liquid water acts as the perfect medium for the chemical reactions that allow life as we know it. Therefore, one of the great mysteries of Kepler-22b is whether it can truly harbour vast oceans of liquid water on its surface. What conditions does this distant world need for water to remain in liquid state and not evaporate or freeze? For water to be liquid on a planet, two fundamental requirements must be met: an adequate temperature and sufficient atmospheric pressure. If the temperature is too low, water freezes. If it is too high and the pressure is low, water evaporates quickly. On Earth, for example, the balance between temperature and pressure allows oceans, lakes, and rivers to exist as we know them. In the case of Kepler-22b, models suggest that its position in the so-called habitable zone the region around its star where temperatures are suitable for liquid water, gives it a unique opportunity. However, is it enough to be in the habitable zone to guarantee the existence of oceans? The answer is not so straightforward. The composition of the atmosphere plays a crucial role. If Kepler-22b has a dense atmosphere composed of gases like carbon dioxide or water vapor, it could retain heat and prevent its oceans from freezing, even if it is a bit farther from its star. Conversely, a too thin atmosphere would not be able to retain heat, and water would end up freezing on the surface. It's like a blanket. The thicker it is, the more heat it retains. Scientists speculate that if Kepler-22b is a mostly watery planet, its atmosphere must be thick enough to maintain adequate pressure and favor the presence of liquid water. What about gravity? A planet with greater gravity than Earth could help retain the atmosphere and, therefore, the water on its surface. But excessive gravity could also affect the circulation of water and gases, generating climatic dynamics completely different from those of our planet. In simple terms, the possibility of liquid water on Kepler-22b depends on a delicate dance between temperature, pressure, and atmospheric composition. Although we cannot yet confirm the existence of endless oceans on this distant world, the theoretical conditions make it one of the most fascinating candidates in the search for life beyond the solar system. Could Kepler-22b be the first alien ocean we discover? For now, the answer remains floating, mysterious, among the stars. Can plate tectonics exist on a planet almost entirely covered by water? That is one of the most fascinating questions when we talk about Kepler-22b. On Earth, plate tectonics is the force that shapes continents, causes earthquakes, and allows for the recycling of essential materials for life. But what happens in a world where, according to hypotheses, there are no continents and the ocean could reach depths of tens of kilometers? To understand this, we must first ask how the interior of such a planet would function. On Earth, internal heat drives the movement of plates, huge fragments of solid rock that float on a partially molten mantle. But on a planet like Kepler-22b, where the pressure of the water is so overwhelming that it could transform ice into exotic forms like so-called Ice 7, the internal dynamics would be radically different. Could there be a rocky crust beneath kilometers of water and ice? Models suggest that yes, but it would be much deeper than on our planet. Many scientists believe that in oceanic worlds, the interaction between water and the mantle could generate geological activity, albeit differently than on Earth. Imagine a planet where, instead of mountain ranges and volcanoes emerging to the surface, tectonic activity occurs beneath a mantle of ice and water. In this scenario, hydrothermal vents, similar to those in Earth's ocean depths, could be common, driven by the planet's internal heat. These vents could create oases of energy and chemical compounds, key ingredients for life, even in the absence of sunlight. However, there is a great mystery. Would the colossal pressure of the ocean prevent the plates from moving as they do here? Some models suggest that the crust of Kepler-22b could be so thick and dense that tectonic movements would be slow or even non-existent. Others propose the possibility of submerged plate tectonics, where the cycle of materials between the mantle and the ocean occurs continuously, but hidden beneath kilometers of water. Would this be enough to maintain nutrient recycling and climate stability, as happens on Earth? It is an open question, but what we do know is that the geology of Kepler-22b could be the key to understanding whether an oceanic world can truly be habitable. Thus, the tectonics and geology of Kepler-22b invite us to reconsider what we understand by active planet. Perhaps, in a world where the ocean covers everything, geological processes are more subtle, yet equally essential for the possibility of life. The great unknown remains how these processes manifest, and whether Kepler-22b hides, beneath its infinite ocean, a geological machinery capable of sustaining a complex ecosystem. Have you ever wondered what it would be like to walk on a planet with a different gravity than Earth? Kepler-22b, being a larger planet than our world, likely has greater gravity. If you jump on our planet and fly for a moment on Kepler-22b, you would barely manage to lift off the ground. Some calculations suggest that its gravity could be between 1.5 to 2 times that of Earth, although there is still no exact measurement. But what would this mean for any form of life that could inhabit there? Stronger gravity has profound effects on biology. Think about terrestrial animals. On Earth, elephants and whales have evolved to support their own weight under Earth's gravity. On Kepler-22b, any living being would need much more robust body structures. Creatures might be shorter and more compact, with dense bones and powerful muscles to withstand the force that keeps them grounded. Even the simple act of lifting a limb, which here seems trivial, would be a constant challenge there. Now, what if the planet is actually covered by an endless ocean, as many scientists suspect? In an aquatic environment, gravity feels different. Water helps support the weight of living beings, allowing larger and bulkier creatures to exist without collapsing under their own weight. However, higher gravity would also mean that the water is denser, and moving through it would require more energy. The marine beings of Kepler-22b might have hydrodynamic bodies, powerful fins, and adaptations to take advantage of buoyancy, but always facing the challenge of persistent gravitational force. And how would that gravity affect a hypothetical human visitor? In an environment with double the gravity, each step would feel like carrying a heavy backpack. The heart would have to work harder to pump blood, bones and muscles would fatigue quickly. And what here is a simple walk could be an exhausting feat there. This raises fascinating questions. Could intelligent life evolve on such a planet? Would it be possible to build advanced civilizations? Or would the energy needed to move and construct limit technological development? Gravity, that invisible but omnipresent phenomenon, could be the decisive factor in the biological and cultural fate of Kepler-22b. Finally, it is worth asking how gravity would influence the evolution of senses and perception. Would the inhabitants of Kepler-22b have a different vision, adapted to move more slowly or perceive their environment differently? Would they develop unique sensory organs to survive in a world where every movement costs more energy? Gravity not only defines the shape and size of life, but also the way living beings interact with their environment. Thus, in the infinite ocean of Kepler-22b, gravity is not just a physical force. It is a silent architect of the destiny of life. When we think about the possibility of life on other planets, atmospheric pressure is a crucial factor. But how different could the experience be on a world like Kepler-22b? On Earth, the atmospheric pressure at sea level is sufficient to maintain liquid water and allow us to breathe without difficulty. But on a planet with an infinite ocean, could we even float on the waves? Or would the pressure be so intense that it would crush any vessel or terrestrial creature? Scientists have debated the possible density and composition of the atmosphere of Kepler-22b, as this determines everything from the depth of its oceans to the stability of its climatic conditions. We know that Kepler-22b is considerably larger than Earth. This size difference implies greater gravity, which in turn could generate a denser atmosphere and a much higher surface pressure. To visualize it, think of the bottom of a deep pool. The deeper you go, the greater the pressure on your body. Now, translate that feeling to a planetary scale. If the atmosphere of Kepler-22b is several times thicker than ours, any living being or vessel attempting to explore its surface, or rather its ocean, would face pressures that could far exceed those of the deepest ocean trenches on Earth. Will there be areas in that ocean where the pressure is so crushing that even the most resilient life forms on Earth could not survive? On our planet, there are organisms that live kilometers underwater, enduring unimaginable pressures. However, if the atmospheric pressure of Kepler-22b is even more extreme, only incredibly adapted life forms could thrive. This raises fascinating questions about the possible biology in such a world. Would the hypothetical inhabitants of Kepler-22b have much more resilient body structures, Or perhaps they would harness the pressure to develop abilities and characteristics that seem impossible here. Atmospheric pressure also plays a determining role in habitability and the existence of liquid water. If it is too low, water would evaporate quickly. If it is too high, it could remain liquid even at unusual temperatures, but at the cost of creating a hostile environment for life as we know it. Furthermore, the high pressure could affect the chemistry of the atmosphere and the formation of clouds, storms, and climate cycles. Thus, the atmospheric pressure on Kepler-22b is not just a curious fact. It is one of the great challenges in imagining what life, climate, and exploration would really be like in this fascinating world of infinite ocean. When we think about the possibility of life on other worlds, one of the first questions that arises is, how much light and energy does that planet receive from its star? In the case of Kepler-22b, the amount of light that reaches its surface is a crucial factor in understanding its climate, its potential to harbor liquid water, and of course, in imagining what a typical day would be like on this distant oceanic world. But does Kepler-22b receive the same amount of sunlight as Earth? The answer is no, and this is where the planet begins to differ from what we know. Kepler-22b is located at a distance from its host star, very similar to that which separates Earth from the Sun. However, the star Kepler-22 is slightly cooler and less luminous than our Sun. As a result, the light that reaches the surface of this exoplanet is less intense than what we enjoy on Earth. To put it in perspective, if on Earth we bask under a high-powered lamp, on Kepler-22b, it would be like being under a dim, yet constant light. This does not mean that the planet is shrouded in darkness. Rather, the energy it receives is sufficient to maintain temperate temperatures if there is a suitable atmosphere, but likely insufficient to generate scorching deserts or intense solar radiation. What is the effect of this softer light on an infinite ocean? On Earth, sunlight penetrates only a few hundred meters into the oceans before fading into darkness. On Kepler-22b, the light from its star, although weaker, could create a warm surface layer, ideal for chemical and biological processes. However, the depths of that ocean would be completely dark, as is the case in our abyssal seas, a mysterious environment where life, if it exists, would have to adapt to the almost total absence of light. But there is another fascinating question. How does the quality of light affect the possible organisms that might arise on Kepler-22b? By receiving less energy and likely a more reddish light, photosynthesis, if it were to exist, would have to be different from that on Earth. Hypothetical life forms could develop pigments adapted to the dim light, much more efficient at capturing the few available photons. This simple detail could influence everything from the color of the oceans to the appearance of any living being from that distant world. Thus, the light and energy that bathe Kepler-22b not only determine its climate, but also open the door to countless possibilities about how a completely different ecosystem from ours could function. Could a lesser amount of energy give rise to slower, more resilient, or even stranger forms of life than we have ever imagined? The answer, for now, remains in the shadows, waiting to be discovered. What would happen if days and nights didn't last the same as on Earth? On Kepler-22b, the length of day and night is one of the great mysteries that intrigue scientists. It is not precisely known how long a complete rotation of this planet lasts, but calculations suggest it could have a very different rhythm than our home. If Kepler-22b rotates slowly, its days and nights would be much longer than those on Earth, creating prolonged periods of light and darkness. Conversely, if its rotation is fast, the cycles would be brief, altering the planet's climate and energy patterns. Now, why is it so relevant to know the duration of day and night in such a distant world? Imagine living in a place where the sun takes weeks or even months to rise and set. This would have profound consequences on surface temperature, winds, and the behavior of the global ocean that is suspected to cover Kepler-22b. If the planet experiences extremely long days, the waters could heat up significantly during the day, and cool down considerably at night, leading to more intense ocean currents and possible gigantic storms. In contrast, short cycles of light and darkness would result in a more stable climate, but with less extreme variations. And what role does the orbit of Kepler-22b play in these cycles? Unlike Earth, whose axial tilt is responsible for the seasons, the uncertainty about the tilt of Kepler-22b leaves many possibilities open. If its axis were highly tilted, entire regions could spend long periods in twilight or under constant light, affecting the potential emergence of life and the dynamics of its atmosphere. Furthermore, if the planet were gravitationally locked to its star, as the Moon is to Earth, one of its halves would be permanently illuminated, while the other would be shrouded in eternal night. This phenomenon, known as tidal locking, would completely change the meaning of day and night. The duration of light and dark cycles would also influence the ocean's chemistry and the availability of energy for any potential life forms. On Earth, organisms have evolved adapting to a regular 24-hour cycle, but on Kepler-22b, life, if it exists, might have to face extreme challenges, such as prolonged periods of photosynthesis or long stages of darkness, where they would rely on alternative energy sources. Deciphering these cycles not only helps us imagine what a day would be like in this distant oceanic world, but also allows us to better understand the limits of habitability beyond our own planet. What would the climate be like on a planet almost entirely covered by a deep and unknown ocean? On Kepler-22b, scientists believe that the global climate would be radically different from that of Earth, precisely because the solid surface, if it exists, would be completely submerged beneath a vast ocean. The absence of large continents means there would be no mountains, deserts, or large expanses of land to disrupt the flow of wind or modify ocean current patterns. In simple terms, the ocean would act as a gigantic thermal blanket, distributing heat much more evenly than on our planet. Is it possible that colossal storms exist on Kepler-22b, even larger than terrestrial hurricanes? The answer could be affirmative. Without the presence of continents to limit the passage of air and water currents, storms would have room to grow unrestricted. Climate models suggest that on oceanic planets, winds can reach extreme speeds, and rains can be persistent, generating storm systems that could last for weeks or even months. Imagine a storm sweeping across the planet without encountering obstacles, continuously feeding off the water vapor from the ocean. And what about temperatures? The vastness of the ocean on Kepler-22b would function as an exceptional thermal regulator, absorbing heat during the day and slowly releasing it at night. This would allow for minimal temperature differences between day and night, creating a more stable and predictable climate. However, the exact temperature would depend on the composition of the atmosphere and the amount of energy received from its star, factors that are still uncertain. But in general, thermal stability would be one of the most notable characteristics of an oceanic world. Could there be zones of extreme weather on this planet? Although the ocean moderates temperatures, the latitude and axial tilt of Kepler-22b would also play a key role. If the planet has a tilt similar to that of Earth, we could expect seasons, although much less pronounced. However, if its axis is more stable or barely tilted, the climate could be surprisingly constant everywhere. The combination of an infinite ocean and a potentially dense atmosphere would make the global climate of Kepler-22b less variable than that of Earth, but not necessarily less spectacular. In such a world, the seasons might be barely perceptible, but the magnitude of its storms and the strength of its winds could surpass any weather phenomenon known on our own planet. In short, the climate of Kepler-22b would be a spectacle of colossal scale, where water and atmosphere interact without the limitations imposed by continents. A planet where regularity and violence combine, resulting in an environment as stable as it is challenging, and as predictable as it is unpredictable in its extremes. What kind of life could arise in a world dominated by an endless ocean? Imagination soars, but science has certain rules. On Kepler-22b, where solid ground may be non-existent, and water extends for kilometers deep, life, if it exists, would be radically different from what we know. Would it be organisms resembling simple terrestrial microbes or entirely new creatures, adapted to the crushing pressure and darkness of the depths? On Earth, marine life thrives from the surface to the abyssal, zones where even sunlight does not penetrate, and organisms like extremophiles demonstrate the ability to survive in extreme conditions. Could something similar happen on Kepler-22b? The key lies in adaptability. On our planet, bacteria and archaea survive near hydrothermal vents, feeding on chemicals instead of sunlight. If Kepler-22b has similar energy sources, such as underwater volcanic activity, we could imagine complex ecosystems beneath its eternal ocean. Is it possible that bioluminescent creatures illuminate the darkness, as in Earth's oceanic abysses? Extreme conditions can give rise to astonishing beings. Gelatinous bodies to withstand pressure, slow metabolism to make the most of any energy source, and perhaps even symbiosis with minerals or gases dissolved in the water. Would life on Kepler-22b necessarily be microscopic? On Earth, oceans host everything from tiny bacteria to giant whales. But without solid land, evolution might favor floating organisms, resembling jellyfish or giant plankton, capable of moving vertically to harness nutrients and energy. Perhaps life here would have shapes and behaviors that seem straight out of a science fiction novel, sphere-shaped creatures, endless filaments, or cooperative colonies, adapted to the currents and the unique chemistry of that alien ocean. Now, how could we detect traces of life in such a distant place, hidden beneath kilometers of water? Scientists are searching for biosignatures, chemical signals, or patterns in the atmosphere that could only be explained by the presence of living organisms. If life has emerged on Kepler-22b, it has likely transformed its environment in some way, whether by generating gases, altering the chemistry of the water, or creating complex structures on the ocean floor. We may never get to see these life forms, but the possibility of their existence opens the door to a universe much more diverse and fascinating than we ever imagined. When we think of ocean planets outside our solar system, it's natural to wonder, is Kepler-22b unique, or are there other similar worlds floating in the vast cosmic ocean? The answer is fascinating. Over the past few years, astronomers have identified several exoplanet candidates that, like Kepler-22b, could be entirely covered by water. What are these other worlds, and how do they resemble or differ from our protagonist? One of the most well-known examples is GJ329c, an exoplanet that orbits a red dwarf star about 20 light-years from Earth. Models suggest that GJ329c could harbor a global ocean beneath a dense atmosphere, although with temperatures and light conditions very different from those of Kepler-22b. Another intriguing case is K2218b, discovered by the Kepler Space Telescope. This world, approximately twice the size of Earth, has shown signs of water vapor in its atmosphere, reinforcing the hypothesis of an ocean planet, albeit with significantly higher pressure and gravity. However, not all ocean exoplanets are the same. Some, like TRAPPIST-1e and TRAPPIST-1f, are part of a system of 7 planets orbiting an ultra-cool star nearly 40 light-years away. On these worlds, water could exist in liquid form, depending on the atmospheric composition and the exact distance to their star. The key difference with Kepler-22b lies in the energy they receive. While TRAPPIST-1e is located in a much colder zone, Kepler-22b receives an amount of light and heat more similar to what Earth experiences, increasing the chances that its ocean is stable and deep. But what makes Kepler-22b special within this select group? Its location in the habitable zone around a Sun-like star and its size, just slightly larger than Earth's, make it one of the most promising candidates for the existence of a temperate global ocean. While other worlds may be too large, have toxic atmospheres, or receive too little stellar energy, Kepler-22b represents a sort of middle ground where conditions could be, at least in theory, compatible with Earth-like life forms. Comparing Kepler-22b with other ocean exoplanets helps us better understand the diversity of possible worlds outside our solar system. Just as Earth's oceans hide secrets and surprising forms of life, there could be countless water-covered planets in the cosmos, each with its own chemical and climatic stories. The search for these worlds is, at its core, a search for our own history, projected in the distant mirror of exoplanets. How many infinite oceans are out there, waiting to be discovered? What does it take to investigate a planet over 600 light-years away? This is one of the big questions that currently motivate scientists around the world. Today, space telescopes like the James Webb and future projects like the Roman Space Telescope promise to revolutionize the way we study exoplanets like Kepler-22b. Thanks to these instruments, we will soon be able to analyze the atmosphere of this distant world and search for traces of molecules like water vapor, methane, or even oxygen. Imagining detecting signs of life at such a distance may seem like science fiction, but every technological advance brings us closer to that goal. Will we ever be able to send a probe to such a planet? For now, the idea of sending a spacecraft to Kepler-22b is a titanic challenge. With current technology, a spacecraft would take tens of millions of years to arrive. However, conceptual projects like Breakthrough Starshot explore the use of solar sails propelled by powerful lasers to achieve unprecedented speeds. Although for now these missions are only proposed for closer stars, research in advanced propulsion could, in the distant future, open the door to actual interstellar exploration. Who knows? Perhaps the first step is to send small robotic probes that transmit data back to Earth. In the meantime, indirect exploration continues to advance. Astronomers rely on innovative techniques like transit analysis and spectroscopy to deduce the composition of the atmosphere, the presence of clouds, and even possible oceans. The use of artificial intelligence allows for processing vast amounts of data and detecting weak signals that would otherwise go unnoticed. Each new algorithm, each improvement in sensors, enables us to imagine more clearly what the surface and climate of Kepler-22b are really like. But what would it mean, in practical terms, to discover signals of a global ocean or even of life? The confirmation of such findings would transform our view of the universe and redirect the search for life in other corners of the galaxy. The future of exoplanet exploration depends as much on human curiosity as on international collaboration and sustained technological development. The study of distant worlds like Kepler-22b is a bridge between current science and humanity's boldest dreams. What seems unattainable today could be as commonplace tomorrow as sending a probe to Mars. Is it possible that one day humans will step onto the surface, or rather, navigate the oceans of Kepler-22b? This question poses one of the greatest challenges of modern space exploration. To begin with, the distance is overwhelming. Kepler-22b is over 600 light-years away from Earth. If we were to use the most advanced technology available today, a journey there would take many generations. Even a spacecraft traveling at a considerable fraction of the speed of light would require colossal infrastructure and resources that we can currently only imagine in science fiction. But let's assume that somehow we overcome the barrier of distance. What obstacles would we encounter upon arrival? Gravity is a first and major challenge. It is estimated that Kepler-22b has a gravity greater than that of Earth, which would greatly complicate any attempts at landing and movement. For the human body, increased gravity could mean constant pressure on bones and muscles, making even walking or standing exhausting. How would astronauts adapt? Would it be necessary to design special suits, or even genetically modify travelers to withstand those conditions? The next big challenge is the infinite ocean that is believed to cover the planet's surface. Unlike exploration on Earth, where we have solid surfaces to land on and establish bases, on Kepler-22b, the absence of solid ground would require the development of entirely new technologies. We would need to build vessels capable of withstanding extreme pressures, unknown storms, and perhaps even ocean currents far more powerful than anything seen on our planet. Additionally, the depth of this ocean could far exceed that of Earth's oceans, presenting an extremely hostile and unknown environment. We cannot forget the atmosphere, which to this day remains a mystery. If it is toxic, too dense, or lacks oxygen, humans would have to live permanently in sealed habitats, as if they were always in a space station floating above an eternal sea. What would happen with the radiation coming from its host star? Without a proper protective atmosphere, radiation could be lethal in a short time. And then there's the logistical question. Every resource, from oxygen to food and energy, would need to be produced locally or transported from Earth, multiplying the complexity of the mission. Finally, the essential question arises: is it worth facing all these obstacles to explore such a distant and hostile world? Human history is full of examples where curiosity and the need to explore have driven unimaginable advancements. However, Kepler-22b represents such an extreme frontier that, for now, we can only dream of its direct exploration. Future technology may give us the tools to overcome these challenges, but in the meantime, imagination and science remain our primary vessels toward the infinite ocean of this mysterious world. What secrets does a planet completely covered by an ocean hold? The answer to this question could transform our understanding of life in the universe. Kepler-22b has sparked a genuine revolution in astrobiology. Located in the habitable zone of its star and potentially an oceanic world, this exoplanet has become a key piece in studying the possibility of life beyond Earth. Why is it so relevant? Because it forces us to rethink the classic parameters of habitability. If here, on our planet, life emerged in the oceans, could this phenomenon be repeated in a similar, albeit much more extreme and distant environment? Astrobiologists face the challenge of imagining forms of life that could evolve in a deep ocean, without solid ground, and perhaps under an atmosphere radically different from ours. What would organisms be like in a sea without shores? What biological adaptations would be necessary to survive in the darkness of the depths or under pressures hundreds of times greater than those at Earth's surface? These questions drive the development of new theories about life, expanding the range of possibilities beyond terrestrial limits. Thus, Kepler-22b serves as a virtual laboratory where scientists can test hypotheses about ecosystems completely foreign to those we know. Another fascinating consequence of studying this planet is the impact on the search for biosignatures. If life on Kepler-22b were possible, what chemical or biological signals could we detect light years away? Researchers are exploring the possibility of tracking specific molecules in the atmosphere, such as oxygen or methane, which on Earth are associated with biological activity. However, they also consider that deep ocean life could generate very different biosignatures, forcing astrobiology to be more creative and less anthropocentric in its search methods. Ultimately, Kepler-22b has broadened the horizon of astrobiology, showing that planetary oceans could be much more common than previously thought. If life can arise and thrive in such distinct environments, are we facing a universe filled with inhabited worlds, each with its own version of biology? The existence of planets like Kepler-22b invites us to continue exploring, posing increasingly bold questions about our place in the cosmos and the diversity of life beyond our terrestrial experience. What role does stellar radiation play in the evolution of a planet like Kepler-22b? When envisioning a world covered by an infinite ocean, it's tempting to imagine a perpetual calm, but the reality is much more complex. The radiation emitted by its host star, Kepler-22, could be both a vital source of energy and a constant threat to the planet's stability and any potential forms of life. On our own planet, sunlight allows entire ecosystems to develop, but it can also cause genetic mutations and damage cells. Does something similar happen at 120 times the distance from the Earth to the Sun? The radiation that Kepler-22b receives largely depends on two factors: the activity of its star and the presence of an atmosphere capable of filtering the most dangerous rays. If Kepler-22 is a calm star, like our Sun, we might expect the planet to receive moderate radiation, enough to maintain suitable temperatures on the surface. However, if the star experiences frequent eruptions or emits large amounts of ultraviolet and X-ray radiation, the consequences would be very different. Could a global ocean act as a natural shield, protecting life beneath its surface? Water is excellent at blocking radiation, so marine organisms could thrive in the deeper layers, away from the direct influence of stellar radiation. But what if the atmosphere of Kepler-22b is thin or lacks the right gases to block radiation? In that case, the ocean's surface would be exposed to intense doses of energy, making the existence of life as we know it on Earth difficult. Excessive radiation can break essential molecules for life, such as DNA, and cause chemical changes in the atmosphere and water. On the other hand, a dense atmosphere rich in elements like ozone or carbon dioxide could act as a natural filter, allowing only the passage of light necessary for photosynthetic processes while blocking harmful rays. Stellar radiation could also influence the chemical composition of the ocean itself. Some essential chemical reactions, such as the formation of organic compounds, depend on energy from starlight. Thus, radiation could be a spark for the emergence of prebiotic processes, as long as its intensity does not exceed certain limits. This delicate balance is reminiscent of a tightrope. Too much radiation could sterilize the planet, but the right amount could be the engine of a complex biosphere. Ultimately, the relationship between Kepler-22b and the radiation from its star is a constant tug-of-war of forces. The fate of potential life on this oceanic world depends on factors we still cannot observe in detail, but which invite us to reflect on how fragile and, at the same time, resilient life in the cosmos can be. Would radiation be an insurmountable obstacle or the catalyst for new forms of existence? The answer remains, for now, as deep and mysterious as the infinite ocean of Kepler-22b. What secrets could an ocean that completely covers the surface of a planet hide? When scientists think of the ocean of Kepler-22b, they do not imagine it as a simple, uniform mass of water. On the contrary, they consider the possibility that this infinite ocean is divided into various layers, each with its own physical and chemical characteristics, much like Earth's oceans, but taken to the extreme. Could there be a surface layer similar to the one we know on Earth, where the light from its star penetrates and determines the temperature and microscopic life? It is likely that the upper layer of this ocean would be the most dynamic, stirred by winds and temperature differences. Here, solar energy could enable processes similar to photosynthesis, if organisms adapted to that environment existed. However, due to the depth and extent of the ocean, light would not reach very far, and in just a few hundred meters, absolute darkness would reign. As we descend, the pressure would increase exponentially. Have you ever wondered what life would be like in an environment where the pressure is hundreds or even thousands of times greater than what we feel on the Earth's surface? In the depths of the ocean of Kepler-22b, temperature and chemical composition could vary dramatically. Some scientists speculate that there could be an intermediate layer, rich in compounds like ammonia or methane, which would act as a natural barrier, separating the surface water from the rest of the ocean and affecting the circulation of nutrients and heat. And if we continue to descend, what would we find at the bottom of this endless ocean? This is where scientific imagination is truly put to the test. There may not be a solid rocky bed like on Earth, but rather a core covered by a dense layer of water in a solid state due to the immense pressure, something akin to Ice 7, an exotic form of ice that only forms under immense pressures. This ice, far from being cold and slippery like the ice we know, would be incredibly dense and hot, preventing liquid water from coming into direct contact with the planetary core. Thus, the infinite ocean of Kepler-22b would not just be a vast sea, but a complex structure formed by overlapping layers, each with its own rules and mysteries. Could life develop in any of these layers, adapting to extreme and unknown conditions for us? These questions open the door to new ways of understanding not only oceanography, but also astrobiology and the diversity of worlds that exist beyond our solar system. What weather phenomena could be triggered on a planet almost entirely covered by water like Kepler-22b? With no large landmasses to interrupt climate patterns, storms are likely to be colossal and persistent. Imagine it. Without continents to slow down the winds, cyclones could travel thousands and thousands of kilometers without encountering resistance, growing in intensity as they absorb energy from the vast ocean. On Earth, hurricanes lose strength when they make landfall, but on Kepler-22b, these systems could evolve to reach unimaginable dimensions, comparable to gigantic planetary whirlwinds that would last for weeks or even months. Could there be perpetual storms on its surface? Theoretical models suggest that yes, the combination of a possibly dense atmosphere and the vast oceanic surface would facilitate the formation of enormous equatorial storms, similar to the large cyclonic systems of Jupiter, though fueled by water rather than light gases. Furthermore, the absence of mountain ranges or continents removes the natural barriers that on Earth typically divide climates and limit the size of weather phenomena. Thus, we could expect superstorms that traverse the planet from one hemisphere to the other, accompanied by torrential rains and extreme wind speeds. And what about the winds? While on Earth the trade winds cross the oceans carrying moisture and forming clouds, on Kepler-22b, this process could be amplified enormously. The solar energy received from its host star would heat the ocean's surface, generating rising air currents and enormous low-pressure systems. This, in turn, would create belts of uninterrupted winds that would circle the planet, dragging along dense clouds and possibly causing constant precipitation in some regions. It is likely that the skies of Kepler-22b are almost always overcast, with thunder rumbling and lightning frequently illuminating the horizon. Could the climate of such a planet be predictable, or would chaos reign? The fascinating thing is that although the weather patterns would be gigantic, they could surprisingly be stable in the long term, much like Jupiter's Great Red Spot. However, the intensity and scale of these phenomena would make Kepler-22b an extreme world, where life, if it exists, would have to adapt to an environment of violent and continuous changes. Ultimately, a planet of infinite ocean would be the stage for spectacular meteorology, far more dramatic and powerful than that of our own world. What would happen to the water cycle on a planet completely covered by ocean with hardly any land? On Kepler-22b, the cycle of evaporation and precipitation would be radically different from what we know on Earth, but no less fascinating. On our planet, oceans and seas constantly evaporate water due to solar heat, forming clouds that later release rain over continents and oceans. But in the case of an oceanic world like Kepler-22b, the entire surface would be available to evaporate water, which could lead to a particularly humid atmosphere and dense clouds covering large expanses of the planet. Could it rain endlessly in such a world? The answer is more complex than it seems. Although a lot of water would evaporate, the balance between evaporation and precipitation would depend on the amount of energy received from its star and how winds circulate in its atmosphere. Without land masses to interrupt the flow, air currents could transport moisture evenly around the planet, making rain almost ubiquitous, but with variations in intensity depending on latitude and season. In the tropics, for example, evaporation would be more intense, while at the poles, precipitation could take the form of snow or ice if temperatures allow. What would a storm be like on Kepler-22b? Without mountains or continents to hinder the passage of clouds, storms could travel thousands of kilometers without obstacles. This could lead to gigantic low-pressure systems and colossal hurricanes, much larger than the most fearsome ones we have seen on Earth. The constant interaction between the warm ocean and the humid atmosphere would fuel an incessant cycle of evaporation, cloud formation, and torrential rains. The planet's surface, far from being a tranquil ocean, would be marked by the presence of almost perpetual storms, capable of transforming the global climate in unpredictable ways. And what consequences would this have for life or geological processes? Such an intense water cycle could influence the salinity and temperature of the ocean, modifying the circulation of its waters and perhaps even affecting the chemistry of the atmosphere. Moreover, the absence of land would prevent the formation of rivers and lakes as we know them, but the constant evaporation and precipitation would maintain a dynamic balance in the ocean. In a world where water never rests, life, if it exists, would have to adapt to an environment in perpetual motion, where rain could be as common and abundant as the very ocean that covers the planet. When we think of natural resources, our minds often travel to the minerals, water, or fuels we find on Earth. But what resources might we find on a planet like Kepler-22b, where the ocean seems endless? The first answer that comes to mind is water, but not just any water. We are talking about a colossal volume, possibly hundreds of times greater than all the Earth's oceans combined. This infinite ocean could hide not only liquid water, but also a variety of dissolved compounds and minerals that we have never seen in our world. Could there be deposits of rare metals in the depths of Kepler-22b, as is the case in the hydrothermal vents on Earth's ocean floors? On our planet, these hotspots harbor valuable minerals and are true oases of life. If the exoplanet has geological activity beneath its ocean, we could imagine vast fields of minerals, perhaps even new elements still unknown to science. The extreme pressure and temperature at those depths could give rise to exotic materials, with properties very different from anything we can find here. Now, what about organic compounds? On Earth, the combination of water and energy sources like volcanic activity has given rise to complex molecules, precursors of life. On Kepler-22b, the infinite ocean could act as a gigantic chemical laboratory. Is it possible that new molecules are formed there, perhaps with applications in biotechnology or medicine that we cannot even imagine? The chemical diversity could be astounding, especially if the atmosphere and the ocean interact to create layers rich in different substances. Equally intriguing is energy. Such a vast ocean would be a natural energy generator. Gigantic tides, underwater currents, and thermal differences between the upper and lower layers. If humanity could ever harness that energy, it would be like accessing an almost inexhaustible battery. But would the pressure and composition of the water be an obstacle or an opportunity to develop new forms of technology? Kepler-22b, with its hidden resources beneath kilometers of water, forces us to rethink what is truly valuable and to dream of possibilities that, for now, only science can begin to decipher. What makes a world like Kepler-22b so fascinating to the human imagination? Perhaps the answer lies in our own history as explorers. Since we first gazed at the horizon of the ocean, we have dreamed of unknown lands, impossible creatures, and civilizations hidden beneath eternal waves. Now, knowing that there is a planet hundreds of light years away, potentially covered by an endless ocean, science fiction finds a perfect canvas to paint alternative futures and question the limits of life. Is it possible that beneath those infinite waters exist ecosystems that surpass our understanding? Authors and filmmakers have played with this idea, imagining underwater civilizations, colossal creatures, and forms of life we would never see on Earth. An oceanic planet like Kepler-22b inspires scenarios worthy of novels like Stanislaw Lem's Solaris, where intelligence takes no human or terrestrial form, or aquatic worlds similar to those in movies like Waterworld, where adaptation is key to survival. In science fiction, the infinite oceans are not just landscapes, but laboratories of ideas where physics, biology, and culture can evolve in totally unexpected ways. Why is the idea of a global ocean so powerful? Perhaps because it symbolizes the unexplored and the mysterious. On Earth, the oceans still hold secrets. A planet entirely covered by water amplifies that feeling to infinity. What technological challenges would we face to explore such a world? Stories imagine submersibles capable of withstanding abyssal pressures, floating cities, or even beings capable of communicating in a language made of vibrations and currents. Science fiction uses these scenarios to question our limits and explore what life might be like in radically different environments. The inspiration offered by Kepler-22b does not stop at the surface. What if the inhabitants of such a world had never seen solid ground? What would their myths, societies, conflicts, and achievements be like? Literature and cinema have taken these questions and turned them into tales of adaptation, survival, and discovery. In the end, the allure of an infinite ocean lies in its potential to challenge everything we think we know about our existence and push us to imagine once again that reality can be as surprising as any fiction. How can we know what a distant world, covered by an infinite ocean, would be like if we have never visited it? The answer lies in the power of computational simulations. Thanks to supercomputers and advanced mathematical models, scientists can create digital versions of planets like Kepler-22b, experimenting with variables ranging from the composition of their atmosphere to the depth of their oceans. It's as if we have a virtual laboratory where we can test conditions impossible to replicate on Earth. Can such a planet sustain hurricane-force winds for years? What would happen if its ocean were deeper than the most remote abyss of our planet? Simulations allow us to explore these scenarios safely and accurately. One of the major challenges is establishing the initial conditions. What temperature do we start the simulation with? How much radiation does the planet receive from its star? Researchers input observational data, such as the planet's size, its distance from its star, and estimates about the atmospheric composition. Then, the simulation calculates how factors like ocean currents, cloud formation, and wind circulation evolve over thousands or even millions of years. It's astonishing to think that, with the right tools, one can observe the evolution of a planetary climate in a matter of hours or days, instead of waiting for real eons. But to what extent can we trust these models? The key lies in comparing them with what we already know. For example, scientists adjust their simulations until they can reproduce known phenomena from Earth or other planets in the solar system. Once the model proves accurate in these cases, it is used to venture into the unknown, like the depths of Kepler-22b. However, there is always a margin of uncertainty, as certain fundamental parameters, such as the exact composition of the ocean or atmospheric density, remain a mystery. Simulations are not crystal balls, but they are reliable maps to guide us in exploring the unknown. Still, the results of these simulations have yielded fascinating ideas. For instance, many models suggest that a global ocean like that of Kepler-22b could have layers of water with different temperatures and chemical compositions, separated by natural barriers, similar to thermoclines in Earth's oceans. Other studies theorize about the existence of gigantic storms that could last for decades, or how the energy from the host star could fuel climate cycles completely different from those on Earth. Thanks to these simulations, every small piece of information helps to build the puzzle of what life and climate might be like on such a distant and mysterious world. What does it mean for humanity to discover a world like Kepler-22b? Beyond the simple fascination with the unknown, this exoplanet represents a kind of cosmic mirror in which we observe ourselves, wondering if we are truly alone in this vast universe. Just as explorers of old ventured across oceans without knowing what they would find on the other side, today our curiosity extends far beyond the confines of the solar system. Kepler-22b is an invitation to imagine new frontiers and to rethink our understanding of life and the place we occupy in the cosmos. Could humanity one day reach a world like this? The distance may seem insurmountable, but human history is marked by overcoming the impossible. The study of Kepler-22b drives the development of new technologies, inspires international scientific alliances, and challenges the limits of our imagination. Every piece of data we obtain, no matter how small, contributes to the construction of a collective knowledge that prepares us for greater challenges, such as interstellar exploration or the eventual search for alternative refuges for the human species. And what if we find signs of life on a planet like this? The impact would be revolutionary, altering our philosophical, ethical, and even religious views on existence. Discovering that the infinite ocean of Kepler-22b harbors forms of life, even if they are microbial, would perhaps be one of the greatest milestones in human history. It would remind us that life, in its infinite diversity, might not be a rarity, but a natural consequence of the right conditions. Humanity would finally have confirmation that it is not unique, and that discovery would forever change our perspective on universal solitude. Ultimately, the importance of Kepler-22b for humanity lies not only in the possibility of finding life, but also in the introspection it provokes. It forces us to value our own planet more, to reflect on the fragility of Earth and the urgency of caring for our oceans and resources. Thus, seeking distant worlds is also a way to understand and protect our home. Kepler-22b is, in essence, a reminder that the human drive to discover knows no bounds, and that every finding in the universe is a new opportunity to question, learn, and evolve as a species. What mysteries still surround Kepler-22b? One of the most intriguing questions is whether that global ocean, which so many scientists imagine, really exists. Although models suggest a water-covered world, we still don't know if it's an endless sea like those in science fiction novels, or if, beneath the surface, submerged continents or unknown structures are hidden. Could there be some kind of solid ground at the bottom? Or are we facing a planet where the water is so deep that it crushes any attempt to compare it to Earth's oceans? Another fundamental question is the nature and composition of its atmosphere. Is it rich in oxygen, like ours? Or do other gases predominate that would make life as we know it impossible? If the planet is shrouded in a dense fog of water, vapor, how does this affect the climate and the possibility of light from its star, reaching the hypothetical creatures that could live there? Without direct data, we can only speculate, but the atmospheric chemistry of Kepler-22b could hide surprises capable of challenging everything we think we know about habitability. Life, of course, is the greatest enigma. If there is an infinite ocean on Kepler-22b, what kind of beings could inhabit it? Would they be similar to Earth's abyssal organisms, adapted to darkness and extreme pressures? Or would evolution take a completely different path, giving rise to unimaginable forms of life? One might even wonder if life in that environment would have a chemical basis similar to ours, or if we would be facing exotic biology based on radically different compounds and processes. Finally, the planet's internal dynamics raise more questions. Is there plate tectonics beneath that endless ocean? If so, how would this affect the planet's stability and its potential to maintain habitable conditions over time? Geological forces could fuel hydrothermal vents similar to those on Earth that are true oases of life in the deep sea. However, without a way to directly observe these processes, we remain in the dark, hoping that future generations of telescopes and probes will someday allow us to unveil the secrets that Kepler-22b still holds. What has recently happened in the study of Kepler-22b that has changed our perception of this mysterious world? In recent years, observational technology has made significant leaps, allowing astronomers to refine the data on this exoplanet. For example, new measurements from the TESS Space Telescope and the analysis of previous data from the Kepler telescope have ruled out the presence of large moons or nearby bodies that could distort the transit of Kepler-22b. This has given scientists greater confidence in the measured parameters, such as its orbital period and approximate size. In turn, thanks to sophisticated artificial intelligence algorithms, small variations in the light from its host star have been detected, which has helped rule out false positives and confirm that, indeed, Kepler-22b is a solid candidate for a potentially habitable planet. But is there any news about the composition of its atmosphere or surface? Although distance remains a considerable obstacle, spectra obtained with ground-based telescopes equipped with adaptive optics have allowed researchers to attempt to break down the light reflected by the system. While it is still not possible to identify specific atmospheric components with certainty, recent simulations suggest that the atmosphere of Kepler-22b could be denser than initially thought. These simulations, based on the brightness and size of the planet, point to the possibility of a gaseous envelope rich in water vapor. If this is confirmed in the future, it would reinforce the hypothesis of a world completely covered by oceans. And what about the search for signs of life, either directly or indirectly? Recently, models have been developed to predict chemical signals that could be detected in the atmospheres of distant exoplanets, and Kepler-22b has been one of the main candidates in these analyses. Scientists have determined which chemical signatures would be the easiest to detect from Earth in the event that active biological processes exist, such as the simultaneous presence of oxygen and methane. While none of these signals have yet been detected on Kepler-22b, advances in planetary spectroscopy are raising expectations. It's like trying to hear a whisper in the midst of a storm, but hope persists thanks to the constant improvement of instruments. Moreover, the development of new space missions, such as the James Webb Telescope and projects still in the design phase, promises a revolution in the observation of exoplanets. The data collected by these instruments could reveal previously unimaginable details about the temperature, atmospheric chemistry, and internal dynamics of worlds like Kepler-22b. In short, each new discovery, no matter how small, serves as a piece of a puzzle that brings us closer to understanding whether, in some corner of the universe, there exists an ocean as vast and deep as that presumed on Kepler-22b, capable of harboring life in forms we can barely imagine. What makes Kepler-22b a benchmark in modern astronomy? To answer this question, it is necessary to analyze the role it occupies among the thousands of exoplanets discovered so far. Kepler-22b was not only one of the first findings in the so-called habitable zone of another star, but it also opened a new chapter in the search for worlds similar to ours. Since its discovery, it has become a sort of emblem for astronomers exploring the possibility of life beyond the solar system. Why? Because it represents the perfect intersection between the known and the unknown. A planet larger than Earth, with potentially suitable conditions for harboring liquid water, but whose exact nature remains a mystery. The impact of Kepler-22b on science is often compared to that of a lighthouse in the fog. Before its detection, the idea of finding a planet in the habitable zone of another star was almost exclusive to science fiction. Now, thanks to this discovery, scientists have a concrete reference to direct their instruments and adjust their models. Kepler-22b acts as a starting point, a tangible example that allows for the evaluation of the odds of finding other similar worlds. Its existence demonstrates that potentially habitable planets are not cosmic rarities, and that the Milky Way could be teeming with candidates. To what extent has Kepler-22b influenced the development of exoplanetary astronomy? Its discovery motivated the creation of new scientific missions and the refinement of observation techniques. It appeared just when technology allowed for the detection of tiny signals in the light of distant stars, teaching astronomers to identify the subtle traces of far-off planets. Thanks to its study, the criteria for defining what habitable means have been refined, and a debate has been sparked about the diversity of ocean planets, super-Earths, and mini-Neptunes. Kepler-22b has become a sort of virtual laboratory to test hypotheses and fuel scientific imagination. Finally, the relevance of Kepler-22b transcends the simple accumulation of astronomical data. Its legacy is to inspire a constant search. How many planets like it exist in our galaxy? Could other worlds harbor forms of life completely different from those we know? By putting our position in the universe into perspective, Kepler-22b reminds us that exploration is, above all, an invitation to question the limits of the possible and to keep an attentive gaze toward that vast ocean of stars that still holds countless secrets. Kepler-22b invites us to look towards the cosmos with a mix of wonder and humility. What possibilities does this water-wrapped world hold over 600 light-years away? As we explore its features, an inevitable question arises. Could this planet be a second chance for life? A distant mirror where nature has rehearsed new forms of existence? Science still has no definitive answers, but the mere fact of discovering a planet with so many similarities and yet so many differences from Earth reminds us that the universe is far more diverse and astonishing than we imagine. Thinking of an infinite ocean covering an entire planet is to envision a scenario where life, if it exists, must have taken unexpected paths. What would ecosystems be like in a sea without shores, without mountains or continents? Perhaps abyssal creatures dominate the depths, adapted to extreme pressures and endless darkness. Or maybe life, if it managed to emerge, finds refuge on the surface, taking advantage of the light from a distant star, similar to the Sun, but with its own nuances. Nothing guarantees that Kepler-22b harbors organisms, but its mere existence broadens our horizon of what is possible. The search for worlds like Kepler-22b is, at its core, a search for ourselves. Are we alone, or is life a common phenomenon in the universe? Each new exoplanet discovered is like a page torn from a great cosmic book that we have yet to finish writing. The finding of a planet in the habitable zone, with potential oceans and temperate temperatures, fuels the hope that one day we may answer one of humanity's oldest questions. Are there other places where life has flourished, even if in radically different forms than we know? Ultimately, the exploration of Kepler-22b is a reminder that curiosity and science are our best tools for deciphering the universe. As technology advances, perhaps we will be able, in the future, to analyze its atmospheres, decipher its climates, and who knows, capture signals of biological processes. For now, Kepler-22b remains a symbol of the unknown, a blue beacon in the vastness of space that challenges us to keep asking, exploring, and dreaming.